All right, now the rest of this chapter we're going to look at a couple other wrinkles in how we're going to be using our balanced equations and our stoichiometry to solve problems. Okay. Um, in chemical reactions, and this is a little bit of a review, we can relate the moles of materials, whether it's reactants or products, to each other. Um, we can say that for every mole of nitrogen that goes in, we get 3 moles of hydrogen that we require for this reaction. 1 mole of nitrogen goes in, and I'll produce 2 moles of ammonia accordingly. All right? So there's different stoichiometric statements that can be made about our about any given chemical reaction that we have. Here's one for you to look at, Fred, and try to solve. Here's a reaction. How many moles of nitrogen gas are used when 2.3 moles of ammonia are produced?
If we produce 2.3 moles of ammonia,
That's right. If I know that I'm going to produce 2.3 moles of ammonia, I can identify how many moles of nitrogen gas are required because there's a stoichiometric relationship between the moles of um, NH3 and moles of ammonia in this reaction. Or sorry, moles of ammonia and moles of nitrogen in this reaction. For every mole of nitrogen, I'm going to produce 2 moles of ammonia. So 2.3 divided by 2 will be my moles of ammonia or nitrogen gas that I would expect to produce. So if 0.575 moles of carbon dioxide is produced by the combustion of propane, how many moles of oxygen are consumed? So here's our balanced equation, and we can answer this question in a very similar manner. What goes to the right of the equal sign here, Fred?
moles of oxygen that are consumed.
Good. Moles of oxygen that are consumed, starting with what?
0.575 moles of carbon dioxide produced.
Very good. 0.575 moles of carbon dioxide produced. And I can relate moles of carbon dioxide to moles of oxygen through the stoichiometry here. 3 moles of carbon dioxide for every 5 moles of oxygen. All right, so 0.575 times 5 divided by 3, that should tell me my moles of oxygen that I would expect to be consumed. See how that works?
Yeah, I see that.
So the coefficients in front here is the stoichiometry that allows us to relate different amounts of the materials or products to each other. We can extend that to masses. How many grams of aluminum oxide are produced when 41.5 grams of aluminum react? All right. Um, if I start with 41.5 grams of aluminum and I want to react that much, how many grams of aluminum oxide am I going to have at the end? Right? Grams of aluminum oxide can relate to my 41.5 grams of aluminum. I can see that the amount of aluminum here relates to the amount of aluminum oxide that I get in my products in a 2-to-1 molar ratio. Now that's not grams, so I have to convert grams of aluminum to moles of aluminum. But then when I have moles of aluminum, I can go from moles of aluminum, 2 moles of aluminum are consumed for every, Al mole of Al2O3 for every mole of aluminum I produced. And then I can go from moles of aluminum oxide, Al2O3, to grams of aluminum oxide, Al2O3. Okay? And then this, I have a molar mass there provided for us, 27 grams per mole. And then here, 101.96 grams for every mole. So 41.5 divided by 27 divided by 2 times 102 should give me my mass of aluminum oxide. Okay? Good. So here's another scenario. How many grams of water would result from the complete reaction of 1.2 grams of H2SO4? All right, how would I go about doing this one, Fred?
Grams of water to the right of the equal sign.
Very good. Grams of water over here. And I start off with 1.2 grams of H2SO4. And I can go from grams of H2SO4 to moles. Why do I want to go to moles?
Because that's how the stoichiometry relates in the equation.
That's right. I can go from moles of H2SO4 to moles of H2O in the equation. And then after I get to moles of H2O, I can go to grams of H2O to identify how many grams I would expect. 18 for every mole. 1 mole of H2SO4 produces 2 moles of water. Do you see that?
That's in the equation, right?
That's right. So 98.08 grams for every mole. So 1.2 divided by 98.08 times 2 times 18. That should be my answer. Okay, so D. Very good. So a lot of that was already review. And here's a little bit more that might be review. What volume of 2 molar HCl is needed to react 25.2 grams of sodium carbonate completely? Well, volume of HCl, that's milliliters of HCl, is that okay?
I guess so.
And I have 25.2 grams of sodium carbonate. And I'm going to go from grams of Na2CO3 to moles, 106 grams for every 1 mole of Na2CO3. And then I can go from moles of Na2CO3 to moles of HCl. Now, I don't have a chemical reaction provided for us.
Well, you can write it, right?
Yeah, I can. I can identify the reaction knowing that I have Na2CO3 reacting with HCl, and my products are going to be NaCl and H2CO3, and the products, or to balance this equation, I'm going to need 2 HCl's and I'm going to produce 2 NaCl's. So that reaction is balanced there, so I can see that 2 moles of this are required for every mole of that. And then I can go from moles of HCl to grams of HCl. Oh, no, I want volume. Moles of HCl here to molarity, it's 2 molar, 2 moles for every 1 liter. And then I can go from liters to milliliters. All right, so 25.2 divided by 106 times 2 divided by 2 times 1,000. 237 milliliters, or 0.237.7 liters. Very good. Excellent. That's a good place to stop.